So then this becomes just IC, just a real axis integration on the kappa plane. Okay? And then you can do integration by parts, because this is an exact integration. And then you can show that by integration by parts, if we assume that the function evaluates to 0 at infinity, then you can get this to become IC minus infinity to infinity ln of f of IC kappa d kappa. Okay, then you can fold this around 0 to infinity ln of f of IC kappa d kappa. So you just need to perform this integration on the real axis of kappa plane, which is actually the imaginary axis of the omega plane. You can pick up all the poles. Okay, you can pick up all the poles and zeros. And so if you're able to find the function that you can put in here, that will replicate all the poles and zeros location in such a way that this sum looks like that sum, then you are done. Okay? So, such a kind of function can be found, like, how would you find the resonant modes of a system? Maybe I can use a simple circuit equivalence to denote this, because I think a full electromagnetics picture would be too complicated to talk about. So if I have an inductor, capacitor, inductor, capacitor, maybe a very complicated looking circuit like this. How do I find the resonant modes of this system? I set up my circuit theory that I learned in my 210, right? Something that you have forgotten long ago. Okay? So you set up a circuit equation, you get this, and you say, usually this is V, but you set V to be 0. There's a definition of resonance. Resonance means that a system can have solution without the presence of the driving force. It's a homogeneous solution to the system. So you can set up a system like this. Then you have this being the resonance solutions. And when would this admit non-trivial solution I? Right, very good. The determinant of Z, which can be varied as a function of frequency, and you vary this as a function of frequency to look for resonant modes. This will have many, many resonant modes. Okay, if I have just a simple system like this, it will only have one resonant mode. But if I increase the order of complexity of my RLC or LC tank circuit, I get many different resonant modes. I can increase the system to be larger and larger. And this can play the role of this function. This can be my f of ICK, or f of omega. Okay? And if I figure out how to find such a function using some other complicated mathematics, then I can substitute that in here and find the Casimir energy. And then after I have found the Casimir energy, I can find the Casimir force. Okay? So it involves a lot of computational electromagnetics, because finding this function in general is not simple. You can do it for circuit theory. For an electromagnetic system, you have to learn some upper level courses to figure out how to find this function. Okay, like method of moments and so on, integral equation solvers, but I just give you a simple illustration of a system where the zeros of this function will give rise to the resonant modes of the system. Okay, I guess I'll stop here. Are there any questions regarding this Casimir force calculation? If not, I guess unless Ayin wants to lecture, I don't feel like lecturing anymore, since we over lecture and give you so many credit. There's a lot of teaching credit for this course since we start.